Hi, I am Dr. Abhishek and in this lecture I am going to discuss about the power spectral density and Gaussian random process. Now let's start with the power spectral density, and in the subsequent lecture we are going to discuss about the Gaussian random process. So what is the power spectral density? Power spectral density means the power content in the signal. So it is denoted by, that is, SXF. So it is nothing but our S with a subscript X, which is our signal, and F denotes the frequency domain. So of a random process, Xt as the ensemble of the power spectral density. So what is the formula? Formula for the power spectral density is given by SXF limit t tends to infinite and the Fourier transform of our signal, that is xt. So Fourier transform of xt is nothing but xtf, and mod will give you the magnitude square divided by t, that is the time period of the signal. Here xtf is the Fourier transform of the time truncated signal or the random process, that is xt, that is equals to xt multiply with the rectangular pulse, because in digital communication we are using rectangular pulses or the binary pulses to transmit our signal. So the xtf is nothing but xt into the rectangular or the time truncated random process. So let's derive the Wienerskinchain theorem. So according to Wienerskinchain theorem, the autocorrelation function, that is Rx tau, because we need the delay, time delay. So if you take the Fourier transform of the autocorrelation function, it is equals to the power spectral density, that is XSF. So let's define the Fourier transform of the signal xtf, that is equals to integration. So this is nothing but the Fourier transform of the signal xt. So that is integration from minus infinite to plus infinite xt t e raised to power minus j omega, or you can say omega equals to 2 pi f t dt, that is equals to integration from, our bit is from minus t by 2 to plus t by 2, that is the interval of our signal xt. So xtf is given by integration minus t by 2 to plus t by 2 xt raised to power minus j 2 pi f t dt. So if you want to take the magnitude square, magnitude, so we have taken the magnitude mod whole square, that is equals to xt of minus f multiply with xt of plus f. So this is how we find the magnitude in the Fourier domain. So let's define these equations, that this is the equation 2, 3 and 4. In the previous slide we have the formula to find the power spectral density. So we can write it as, that is integration from minus t by 2 to plus t by 2 at the time instant xt1 e raised to power j 2 pi f t1 dt1 for the first time instant. Similarly, we have to multiply it with the second time instant. Let's see, that is minus t by 2 to plus t by 2 x of t2 e raised to power j 2 pi f t2 dt2. This is the function, or you can say the Fourier transform at the second time instant. So we can write it as integration from minus t by 2 to plus t by 2, then our, and the second integral, that is from minus t by 2 to plus t by 2 x of t1, that is at time instant t1, and multiply with x t2, that is for the second time instant that is xt2, and these two are multiplied, that is e raised to power j 2 pi f t1 and e raised to power j minus e raised to power j 2 pi f t2. So it becomes e raised to power minus j 2 pi f t2 minus t1 dt1 for the first time instant, dt2 for the second time instant. Now let's write the power spectral density given by xxf, that is equals to limit t tends to infinite, and this is the formula, or this is the equation 1 which we have already discussed in the start of the lecture. So it is given by xtf magnitude whole square divided by t. So substituting the value of this Fourier transform xtf from equation number 4, we get, that is limit t tends to infinite 1 by t integration from minus t by 2 to plus t by 2, and second integral for the second time instant minus t by 2 to plus t by 2 xt1 xt2, and the equation e raised to power minus j 2 pi f t2 minus t1 differential dt1 and dt2. So the power spectral density, for the solving it, we are getting limit t tends to infinite for the infinite duration of the time we have, that is 1 by t, this is the factor, and integral from minus t by 2 to plus t by 2, second integral minus t by 2 to plus t by 2 xt1 into xt2 e raised to power minus j 2 pi f t2 minus t1 dt1 dt2. Now we know that the autocorrelation function is nothing but the average of the multiplication of two signals. So here we have the two time instant, or the process at two time instants are multiplied. So this is nothing but the autocorrelation function according to the definition of autocorrelation function. So we can write that the multiplication xt1 into xt2 is the autocorrelation function Rx t2 minus t1. So this is the autocorrelation function at the time instant t1 and t2. Okay. So we can further solve it, that is limit t tends to infinite 1 by t1 integral from minus t by 2 to plus t by 2, and second integral minus t by 2 to plus t by 2 Rx, that is the autocorrelation function of the time difference t2 minus t1, and e raised to power minus j 2 pi f t2 minus t1, that is the time difference, and the differentials are dt1 and dt2. So the autocorrelation function according to the definition is given by Rx, that is t2 minus t1 can be written as the random process x at t1 multiply with the random process x at t2 and the whole average. The same can be written in this form as expectation of x t1 into x t2. So both are the same things. It doesn't make any difference whether you are using the whole bar or you are writing the expectation. Both are the same things. So we can write that is an autocorrelation function, that is Rx t2 minus t1 e raised to power minus j 2 pi f t2 minus t1. We are defining with another variable, that is phi t2 minus t1. So we have this xxf, that is limit t tends to infinite 1 by t integral minus t by 2 to plus t by 2, second integral minus t by 2 to plus t by 2 phi of t2 minus t1 dt1 dt2. So this is the power spectral density of the random process xt at the two time instant, that is t2 and t1. With the help of the autocorrelation function we can find the power spectral density, because according to this theorem the autocorrelation function, the Fourier transform of autocorrelation function is the power spectral density. We'll prove it further. So as we can see from the figure, so we are deriving the Wienerskinchain theorem. For this, we have defined the two time instant, and we are defining the time instant t1 and time instant t2 at the two axes of the coordinate system. So here we are plotting t1 and here we are plotting t2. So here we can see that duration, time duration for this t1 time instant is given by minus t by 2 to plus t by 2. That is the range of the integral. As we can see, the time instant t2 is again having the range that is from minus t by 2 to plus t by 2. So again we have the second integral. So when we are finding the integral, we are finding the area under the curve. So this is the area of this square because the range of the time is same. But if the signal is having some delay, so delay is given by the factor tau, and if it is the addition of the fractional delay, we have tau plus del of tau. So this will be giving the fractional delay. The same delay we are getting on t1. So here we can find that is this is a tau, and this is the point for tau plus del of tau. So if we draw the line intersecting these 2 points, that is tau and this point, so this is given by the equation of the line, that is the time difference t2 minus t1, that is equals to tau. When we are joining the line, or the line intersecting these 2 points is given by, that is the point is tau plus del tau, and here is del tau plus tau. So this is again equals to the time difference, that is t2 minus t1. Now let's define the power spectral density. So the power spectral density xxf is given by limit t tends to infinite 1 by t, and integral is from minus t to plus t, and phi which we have defined in our previous slide, and t minus the magnitude of the delay, that is tau. So the magnitude of delay we have taken because the delay can be a positive delay or a negative delay. Means it may be advance or it may be lag. Accordingly, we have the delay of the process. So we had defined, that is limit t tends to infinite, integral is from minus t by 2 to plus t by 2, phi of tau, and we have taken this t common from this equation, and this t will be cancelled out by this term 1 by t, or the same can be this 1 by t we can take inside the bracket. We are getting 1 minus tau mod of tau divided by t. But here we can see we have this limit, that is t tends to infinite. When you are substituting the limit in this expression, what we are getting is, we are getting that is 1 by t, and 1 by infinite we know it is equals to 0. So this term will be equals to 0. Okay. Now what is left is, that is xxf, that is equals to minus infinite to plus infinite, and phi of tau d tau. So this is our power spectral density in terms of phi. So we can define, that is xsf, that is equals to the integral from minus infinite to plus infinite autocorrelation function rx tau e raised to power j 2 pi f tau d tau. So this means the Fourier transform of the autocorrelation function is nothing but the power spectral density. So this is the autocorrelation function. Now we can define the PSD of the wide sense stationary random process is the Fourier transform of its autocorrelation function. So that is why we are calling this derivation by the name, that is the Wienerskinchain theorem. So this is the derivation which is used to define how we can find the Fourier transform, how we can take the Fourier transform of the autocorrelation function, and we can find the power spectral density. So the autocorrelation function Rx tau for the real process is an even function, because we know that the autocorrelation function is having this curve which have the even symmetry. Whatever area we have on the left hand side or the negative axis of tau, the same area is covered by the right hand side of this. So that is for the positive delay. So this is the autocorrelation function. So as we can see, it is having the even symmetry. So that's why we are calling it as an even function of tau, which is the delay. So this can be proved in two ways. The first is, that is xt of f whole square. We are writing that is a magnitude is equals to xt of f, and xt of f that is equals to xt of f for the positive frequency, xt of minus f for the negative frequency. So if you are converting this autocorrelation function in the Fourier domain, the same we are getting, that is a even function. If we are finding the Fourier transform of this, again this xf is also having the even symmetry. So it is also even function of f. So xf is also even function of f, and Rx tau is inverse transform is also even function of tau. This means if we are again taking the inverse Fourier transform of the power spectral density, it will be again the even function, that is Rx of tau. So we can prove it, that is Rx tau, that is for the positive delay, is given by the expectation, or you can say whole bar of xt and xt plus tau. For the negative delay, Rx of minus tau can be written as xt minus tau by this equation. So if we are finding, or we are taking the third variable, that is t minus tau equals to sigma. So if t minus tau equals to sigma, then the autocorrelation function for the negative delay, that is Rx of minus tau, can be written as, that is x of sigma, and x sigma plus tau, that is equals to Rx of tau. So the power spectral density, that is xf, is a real and the even function of f. This means tau is equals to 0. So if we are substituting tau equals to 0 here, so what we will get? This means this xt we have, and here we will substituting tau equals to 0. So again it will become xt. So xt into xt. So here we can write it as Rx tau, that is equals to tau equals to 0. So it is whole bar, or you can say average, or you can say expectation, all are the same things. So it is xt plus 0 whole bar, that is equals to the expectation or the whole bar xt into xt. So it becomes x square t. So this is nothing but the energy of the signal, that is x square t whole square, or you can say the expectation. So Rx0 equals to the x square whole bar. So this is the autocorrelation function when delay is equals to 0. So a random process xt is said to be, now the next topic is the Gaussian random process. Previously we have seen how to find the power spectral density using the autocorrelation function. This is the second topic of this lecture, that is a Gaussian random process. A random process xt is said to be the Gaussian if the random variable, we have the random variable at different time instant xt1, xt2 up to xtn are jointly Gaussian for every n and for every set, that is t1, t2 up to the time instant tn. So hence the joint PDF of the random process, random variable at xt1, xt2 and xtn of the Gaussian random process is given by the following equation. So we can write the Gaussian random process as the PDF in form of the PDF, that is p at the variable x1, x2, x3 up to xn for the time instant x1, x2 up to xn can be defined as 1 by 2 pi raised to power n by 2 and under root, that is determinant of the covariance matrix kx and exponential of minus 1 by 2 x minus x bar and the transpose of this matrix. So first we have to find the matrix, then the transpose of the matrix. So that is equals to the covariance matrix, that is inverse covariance matrix. So this is inverse covariance matrix x minus x bar. So we have to take the difference with the mean and we have to find the inverse of this matrix, then we will get the covariance matrix. So we can define the covariance matrix by kx, that is equals to x minus x bar multiply with x minus x bar and the transpose of this matrix. So we have to take the transpose, means rows will be converted to columns and whole bar. So we can define the covariance matrix, that is sigma 11, sigma 12 up to sigma 1n, sigma 21, sigma 22 up to sigma 2n, sigma n1, sigma n2 up to sigma nn, and that is defined by the random process xi and xj. So the covariance we can find, that is sigma ij, that is equals to xi minus xj bar multiply with xj minus xj whole bar. So we can define this covariance matrix. So the mean of the covariance matrix kx are specified by xti, that and sigma ij, that is the autocorrelation function rx t1 ti comma tj minus xti into xtj. So this shows the Gaussian random process is completely specified by its autocorrelation function rx ti comma tj and its mean value xt whole bar. The two additional conditions for the wide sense stationary process, as we know, we have discussed in our previous lecture as well, that is rx ti comma tj, that is equals to rx ti minus tj, that is a time difference, and the mean should be constant. So constant for all t. So these are the two conditions of wide sense stationary random process which we have discussed in our previous lecture as well. So what are the properties of Gaussian random process? The Gaussian random process is completely specified by its autocorrelation function. This is the first property, and the mean value. So if the Gaussian random process is wide sense stationary process having the two conditions, that is one is the autocorrelation function and mean is constant, then it is the stationary in the strict sense. So if we are talking about the wide sense stationary Gaussian random process, this means it is strict sense stationary Gaussian random process. So the process of the linear system to the Gaussian random process is also the Gaussian random process. So another significant property of the Gaussian process is that the response of the linear system to a Gaussian process is also a Gaussian process. Let xt be the Gaussian applied to the input of the linear system whose unit impulse response st, if yt is the output response. So we can find the yt is given by integral minus infinite to infinite xt minus tau h of tau d tau yt, that is limit del tau equals to 0. So this we have this yt given by this expression. So in this lecture we have covered the power spectral density, that is a Wienerskinchain theorem, and we have discussed about the Gaussian random process. So thank you.